We're going to just today talk about how to analyze circuits with op-amps in them. These would be ideal op-amps that all have negative feedback, that all follow the rules about basically how we treat them. I am going to go over something before we start because this is something that's covered in Circuits 1, but not in great detail and seems stupid when you cover it anyway. But it's actually quite useful in here, and that is the idea of superposition. So I'm actually going to do that first. Basically, when we analyze op-amp circuits, we use Ohm's law, obviously, and we use nodal analysis sometimes. KVL and KCL always work because in all circuits they will. And we'll use nodal analysis and superposition. And superposition is what we will use the most. So I'm going to go over superposition just briefly and show you an example from Circuits 1, which shows why it seems useless, but it's actually quite useful for op-amp circuits. So, superposition basically states that if you have a circuit with multiple inputs, voltage inputs, current inputs, whatever, that you can analyze the circuit for each particular independent source and then sum your results together and get the final value if you want the voltage or the current in a certain, element. There we go. In a certain element. You can't do this with power. That's not something so you can't, if you wanted to find the power in a resistor, you can't find the power dissipated by each one and add those up. That doesn't work. But voltage and current works the same way. So the general methodology is we turn off all the sources except one, analyze the circuit with just one source, repeat until all the sources have been turned on individually, and then sum the results, which for a complicated resistive network is a real pain because basically you're doing completely different analysis every time and you have to do it over and over and over again. But for op-amp circuits, once you do the analysis once for one input, oftentimes you can say, okay, for this input and this input, it's going to be the same result because of the way the circuits end up working out. So regular circuits are time consuming, and I'm going to show you an example with a regular circuit, although it's a regular circuit in which superposition actually kind of makes sense. But for op-amp circuits, as I said, it will actually save you a great deal of time once we figure out kind of how particular op-amp circuits work. Once we turn off all the sources but one, we'll end up with a circuit we've already analyzed, and then it makes it a little bit easier. So the first example I'm going to do is just using superposition to find the current in the 20 kilo ohm resistor. There are many ways one could solve this that don't involve superposition, but for today, superposition is going to work pretty well. So the first thing we're going to do is we're going to turn off the current source, and when you turn off a current source, it basically just turns into an open circuit, so it goes away. That's what current sources do. They go away when you turn them off, or they leave an open circuit. So what we're left with is just a series circuit, which makes it really easy to find the current in the 2 kilo ohm resistor from the voltage source. So we just basically take 20 and divide by 2K and we get 4 milliamps. So that's how much current is in that resistor that is due to the 20 volt source. The next thing we're going to do is turn off the voltage source, put the current source back in. Voltage sources look like short circuits when you short them. That's what 0 volts is. So we put the current source back and we just short the voltage source, and that gives us no voltage, and so it's out of the circuit. And now we just have current division, basically. We want to find the current through the 2 kilo ohm resistor. We've got 5 milliamps going into a junction and the current splitting in two. So we can use current division, which takes the parallel equivalent of the two resistors, the 2K and the 3K, and divides by the resistor that you want to find the current in. and multiply by the total current. And when we do that, we get 3 milliamps from the 5 milliamp source. So then all we do is we sum the results together to get the total current. So we go back and we take the two values we found, we add them together, and we get the total current. So that's just a very simple example of how superposition works. It will be even easier when we're doing it with OpAmp circuits, but that's just the general concept of what we do. We look at one source at a time. In OpAmp circuits, they will generally all be voltage sources. So basically, anything that is a voltage in will become a short to ground when we turn it off. So let's look at what is the most common OpAmp circuit in existence. In fact, a whole lot of circuits that we'd make out of OpAmps are based on this circuit configuration. This is known as an inverting OpAmp circuit. You'll notice that it has feedback from V out to V minus. So V out is connected through R2 to the inverting terminal, so that is negative feedback. And then we have another resistor that goes to the in. So first of all, what we want to know is the output voltage. That's really the point of amplifiers, is if we put a value in, what do we get out? What we need for this, because it's an amplifier, we need to figure out what the voltage gain is. And remember, voltage gain is just defined as V out over V in. We are not going to find out V out or V in this. We're going to actually solve for that ratio. So when you're finding voltage gain, the point is not usually, unless you're in the lab, is not to measure V out and V in. That's not the point. The point is to find a way to calculate the gain so that when you're given V in, you can automatically get V out. That's the whole point of finding the gain. So we want to find a way to find the gain so that when we look at the circuit, then we know whatever voltage comes in, this is what I'm going to get out. So that's the point of the exercise. The only time you would ever take V out and divide by V in is if you're in the lab and you make a measurement and you measure V out and you know what V in is, and you determine what the gain is from that and see if it matches what you expected it to be. So analytically, we don't go solve for V out in these circuits. We just find a way to figure out the gain without that. So looking at this circuit, first of all, remember the current into the inputs is 0. So we treat that as there's no current going in there. And we also have that V minus is going to equal V plus. So V plus is actually at 0 volts. It's grounded. And what this means is that that 0 volts actually appears at that inverting terminal. That's something known as a virtual ground. It's not actually connected to ground, but that point is 0 volts. What it means is that current can go through that point, so it can go from V out through R2, through 0, back to V in, and current will flow, but there is no voltage, or there's 0 volts at the negative terminal. So we can mark what values we have for IR1. And if you look at IR1, it's just Vn over R1. The cool thing about OpAmp circuits is the Ohm's law part is really, really easy. So we know what IR1 equals. We can also put IR2 in. It is going in the opposite direction because V out we are assuming is going to be bigger than 0. We don't really know that, but the way it's drawn, we're just going to make that assumption. So IR2 is just V out over R2. Now that we have everything marked, we know what IR1 is, and we know what IR2 is, and we have a V in and a V out. If we just combine those two, we can get a ratio that will give us what the value of the gain is. And in this case, we know that IR1 is minus IR2. They're marked, they're going in opposite directions. So one of them, if I want to equate them, is going to have to be listed as negative. And That means I can just take those values, Vn over R1 equals minus V out over R2, and move things around a little bit, and I get V out over Vn is minus R2 over R1. That is the value of the gain. That will always be the value of the gain. You actually never need to analyze this particular circuit again, because if you see this configuration, the gain of this configuration is always going to be minus R2 over R1. And the cool thing is, if you build one of these, the gain is almost exactly what you think it's going to be. It's really going to be real, real close. Unlike a lot of circuits that you build where the values you get are kind of off, this should not vary except for the fact that some of the elements are not going to be quite the same as far as resistor tolerance goes. That's the only place that you'll have kind of error coming in. So when you see this configuration, you can just look at it and know that V out over Vn is just going to be minus R2 over R1. We call R2 the feedback resistor. It will occasionally be marked as RF. Sometimes it is. Sometimes it's marked as R2. So don't get fooled into thinking that you use what's labeled as R2. Just whatever the feedback resistor is over whatever the series resistor is, that's going to give you that value. So now that you have memorized that one, hopefully, we're going to do something else. We're going to take the voltage, and all we're going to do is we're going to move the voltage input to the other terminal. So we're basically just going to take those points and switch them. So now we have Vn at the non-inverting terminal, and we have R1 grounded at the other end. And that's going to make a slightly different circuit. This is the second most common type of amplifier you'll see. So once we get done with this, you can just memorize the gain value and not have to reanalyze the circuit. So at this point, it's a little bit different. First of all, Vn is now what is at those points between at the negative terminal, I guess. Since V plus and V minus have to be equal, and Vn is at V plus, that means it's also at V minus. So though we don't have a virtual ground this time, we just have Vn at that point. So we just mark it, and we can mark the current values. We can start with IR1. Now IR1 is just Vn over R1. So that's actually the same thing we got last time. It's just the current direction is the other way. And for R2, now what we have, the voltage across R2 is now V out minus Vn. That's the biggest difference between those two circuits, is that IR2 is V out minus Vn over R2. But they're going in the same direction this time. So I can set them equal to each other and not put a negative sign in because they're both marked as going the same direction. So again, we can get Vn over R1 equals V out minus Vn over R2. And if we move that around, we get V out over Vn equals 1 plus R2 over R1. Something to notice about this circuit. The last circuit, when it was minus R2 over R1, we can have any ratio in the world. We can have a gain of 10. We can have a gain of 1/10. The negative sign actually means when you send an AC signal through, it gets flipped over at the output. If you send a DC signal through, you actually do get a negative number. So if you put 5 volts in and it has a gain of 2, you'll get negative 10 out. For this type, a non-inverting type, the lowest possible gain you can have is 1. You can't ever have less than 1. If you were to completely eliminate R2 and R1 out of the circuit, you would have a feedback loop that, and we'll cover that in a minute, that would give you a gain of 1. But that's the only thing, that's the lowest gain you can have for a non-inverting amp is 1. So that's the gain for a non-inverting amp. So, just summarizing, this is what you should remember out of what we just did. Inverting amps flip V out over. So V out ends up flipped from V in. Non-inverting, they are not flipped. And when we did the LT Spice exercise, you were asked if something was inverting or non-inverting, and that's basically what it means. Either the output's flipped or the output is not flipped. OpAmp amplifiers can amplify DC, which is different from most amplifiers. Most amplifiers can't process a DC signal. OpAmps can. You can actually send a DC signal in and get the gain times the output. The only limit on an OpAmp amplifier is the DC inputs you put in. So you can't get out more than usually plus 15 or minus 15 in the output or the space between. So now we're going to spend the rest of the time looking at several other OpAmp circuits, but they're all based on the first two we did. They will either be based on a non-inverting or inverting OpAmp and have a combination of the two. There will always be negative feedback, and we're just going to look at sort of how we would solve them relatively easily. So the first thing we're going to look at is something known as an inverting weighted summer. This has 3 voltages in, and you'll notice that R2 is now labeled RF because that's the feedback resistor. And it basically takes a number of inputs and combines them. That's what it's good for. And it's also weighted. So depending on your values of R1, R2, and R3, you can increase one more than you increase the other. That's why it's called a weighted summer, because you can basically increase VN1 by 1 and then increase VN2 by 10 and then reduce VN3 if you wanted to. So that's basically why it's useful. This is one of the situations where we use superposition. Superposition is a good way to figure this out and how to analyze this circuit. So first of all, we're just going to look at one input by itself, which means that VN1 is going to be on, and we're going to turn off VN2 and VN3. And when we do that, we short them to ground. So they disappear, and there's a ground connection going to ground. Well, what happens to R2 and R3? What ends up happening, you've got 0 volts at the positive terminal and 0 volts at that grounding point, and they basically, Vn minus or V minus is just going to be 0, but then at the other side of those two resistors, you're also going to have 0. If you have 0 volts on both sides of the resistor, it's as if they don't exist, because there's no current going to go through there, there's no voltage going to be dropped, they're just sitting there, which means they basically just go away. They're like in parallel with 0 volts across them. And that means that they have absolutely no effect on the circuit, which is really cool because we can just like completely eliminate them. And then what do we have left? We have an inverting OpAmp. We already solved that, which is good. So we already know what the first voltage output would be based on what we know about inverting OpAmps. So we know that the first output due to VN1 is going to be minus RF over R1 times whatever VN1 is. So the cool thing is the other two voltage sources are going to have the exact same thing happen. If we have 2 of them shorted, the one that's left is just going to be a regular inverting OpAmp circuit. That's why superposition works so well with OpAmp circuits, because once you've done one, it's going to look exactly the same coming in the other two. So the other 2 inputs, we get the exact same thing. For V double prime out, we get minus RF over R2 times VN2, and then for VN3, we get the same thing again, minus RF over R3 times VN3. So all we need to do is add all that together, and then we know what the output is. Usually the standard convention, because everyone's got a negative sign in front of it, usually we put the negative way out in front, and we just put them in brackets and just have the ratios and have the negative out in front. Just don't forget there's a negative there. And once we do that, we can, if we know the feedback values and we know the resistor values, we can figure out, we don't need to necessarily redo this again ever in your life if you get it the first time. So if there's 25 inputs, it's just going to be the sum of the ratios for each one 25 times. You don't have to reanalyze it 25 times or 100 times or whatever. So forever how many inputs come into this inverting amplifier, you're just going to add up whatever the results of those are. The next time, or the next kind I'm going to look at is the simplest OpAmp circuit you've ever seen. It's really, really simple. It's called a unity gain amplifier. All this does is it works generally as a buffer. Remember 2 weeks ago we talked about input resistance and output resistance of amplifiers and how they affect how the circuit works. And if your input resistance to an amplifier is really, really low, you can lose a lot of signal trying to put signal in. So this type of circuit is used as a buffer between different stages of amplification because it has an infinite input impedance and zero output impedance. So basically it allows an amplifier that is outputting a signal that wants to put a signal into an amplifier that has a really low input resistance. It basically eliminates the need for losing a lot of voltage. So we basically call that a buffer, and we use it as a buffer. And what this means is Vin is just the same as Vout in this particular circuit because Vin is getting put in and the negative and positive terminals have the exact same voltage and the negative input is shorted to the output. So that's all it is. Whatever you put in, that's what you get out. I think you build one in lab one day, from what I remember. So easiest circuit in the world, has no resistors, no nothing. Just connect a wire from pin 6 to pin 2 and put your input at pin 3 and you're done. Really easy. The last one I'm going to do is a combination of inverting and non-inverting circuits. And this is known as a difference amplifier. A difference amplifier has two inputs, but you'll notice that they do not both go into the inverting terminal. One goes into the inverting and one goes into the non-inverting. So we are going to do superposition again, but we'll get different results each time because now you don't have everything going into the inverting terminal. So this is another way to use superposition to our benefit. So we'll start with Vn1, which means that we are going to ground V2. And once we do that, we're going to end up with two nodes at that input. We end up with one node at the non-inverting terminal and we end up with a node at ground, which means that R3 and R4 are in parallel. So we can combine them. But once we do that, how much current is actually going through them? I'm sure you guys all know. Zero. Exactly. Which means that they don't matter in this particular configuration. For right now, for Vn1, they do not affect the circuit at all. As we will see next time, there are times when you put a resistor in that place in an inverting OpAmp, and it doesn't look like it has a use, but it does, but it's not involved in the circuit analysis, and I'll explain where that comes from later, but not today. So for circuit analysis purposes today, we don't need R3 and R4 when we're figuring out the effects of Vn1. And what we have with Vn1 is, again, just an inverting amp. So we know what Vout prime is going to be. It's going to be minus R2 over R1 times Vn1. So that's half the problem. That's the easy half. The other half is a little more complicated, but not terrible. So now we're going to look at VN2. Go back to the original circuit, and we're going to ground VN1, which is semi-unremarkable because we basically have an inverting op-amp circuit, a non-inverting op-amp circuit, and we have to actually kind of find two stages of this to make it work, but it's not too bad. So first of all, we need to find out what V plus is going to be. That's going to be the value that actually goes into the inverting terminal. And remember that there's no current flowing in there, which means that what we have at V plus is just a voltage divider. The current is just going to flow straight through like that. So V plus is just going to be the division between R3 and R4. So to find that, we just have R4 over R3 plus R4 times VN2. And once we've figured that out, we can actually get rid of that whole part of the circuit, because once we get V plus, we don't need the part behind it. So we can actually kind of just get rid of that part. And now what we have is a non-inverting amp, for which we've already found the solution. So again, we can find V double prime out as just being 1 plus R2 over R1 times V plus. And then we found what V plus was, so all we do is substitute that value in. We put the circuit back in, and that is the whole equation that describes V double prime out. And to find the total, all we're going to do is put them together. If we sum the results of V plus and V minus, we just get this kind of long equation. If you set these resistor values to certain values, so basically if you create a situation in which R2 equals R1, so if R2 equals R1, I believe, and R3 equals R4, then if R3 equals R4, we get 1/2 for R4 over R3 plus R4, right? And if we have R2 and R1 equal, we get 1 plus 1 times V in 2. And then we get 1 V in 1. So basically what we get is V in 2 minus V in 1, which is why they call it a difference amplifier, because if you set the resistors just right, you can just have the two voltages going in and just creating a difference between the two. So if R2 and R1 are equal and R3 and R4 are equal, then you can create an amplifier in which it's just the two voltages and the difference between them that is being processed. It's basically just going to give you the difference between the two, which is why we call it a difference amplifier. Yes?
Would that affect the signal if you put in, like, say, two different signals into it? Would it just be voltage, or would it matter?
It would affect the signal, meaning...
Yeah, like, say, two different frequencies, so they see.
Oh, you don't want to do that.
Okay.
The idea of sending in two different frequencies is something that can be explored at a much, much, much higher level, but not so much in here. We assume that they will all be the same frequency, and usually they are, because usually you're processing signals that, pretty much. But yeah, if you have multi-frequency signals, then there is going to be an interaction between them going through. So yes. But we don't talk about frequency in here. We pretend that everything works the same way, which is, other classes cover that kind of thing. So the things we've covered is just the inverting amp, for which you will see many, many more applications of that and many more circuits that are based on that next week. And then the unity gain amplifier, the non-inverting amplifier, the difference amplifier. All of these are basically just based on inverting and non-inverting kind of configurations. And the inverting configuration, when we talk next week, we'll talk about what would happen if you took a different kind of element like a capacitor or inductor. We don't use inductors because they're too big and lossy, but a capacitor, and use that in place of one of the resistors, and you get some interesting circuits when you do that. The rest of this week, I will talk about what happens in op-amps that aren't ideal and some practical considerations. And then I'll very briefly review something about filters, which sometimes people remember and sometimes don't remember from previous classes. But when I talk about stuff next week, you'll have to understand like Bode plots and that kind of thing. So most of the actual problems you're going to be working on are going to be based on this lecture, not so much the next ones that I do this week. So the practical considerations, and then filters is kind of a review. On D2L, I think it's in this week's stuff, may have been last week's, but there's a link to OpAmp practice problems, and there's a sheet of paper that has about 15 problems, I can't remember exactly how many, that are really good practice problems, and the solutions are also there if you want to try them. That particular sheet of OpAmp problems has been floating around here since I was a student and before. So it's like literally the exact same piece of paper been copied, and it was developed by a guy who used to be a professor here, whose last name was Wojnowiak, and he was here for many years, and he was very difficult, and he was the one professor that would give out super Fs if we were in his class. If you got less than a 40 on a test, he would put SF, and he would even give the statistics of how many super Fs occurred in his class. But he would curve at the end, at the very end, when everybody thought they were going to fail. But anyway, he developed this sheet of OpAmp practice problems, and they're really good just to get, practice in actually solving these problems. So I would suggest you go in and kind of practice them. And like I said, the solutions are there, so you can see if you get the right answer. And the idea is always to create a net, just a bunch of resistors together to calculate the gain values. That's your overall goal, is to have all the resistors in the circuit as part of your gain equation and nothing else. With a difference amplifier, we can also look at the relationship between the differential mode voltage and the common mode voltage by taking the V1 and V2 and substituting in what we know about the common mode and differential mode voltages related to those two inputs. So remember that previously we said that V1 was the common mode voltage minus half of the differential voltage, and V2 is the common mode voltage plus half the differential voltage. So if we substitute that into the difference amplifier gain equation, we get the first value that was multiplied by V1 and the second value multiplied by V2, but now we've actually got kind of a mixture of VICM and VIDs, which we just need to separate out. And this is just algebraic. When we go through and do that, we have a bunch of resistor ratios times the common mode voltage minus 1/2 times a bunch of resistor ratios times the differential mode voltage. And the resistor ratio combination in front of VICM is just the common mode gain, and that same resistor ratio times 1/2, which is a little different because it's got a plus R2 over R1 versus a minus R2 and R1, will give you the differential mode gain. We look at the magnitudes of the gain, not the sign, so the negative sign is in there, but we're really not going to use that. So the differential mode gain indicates how much the difference between the input signals is amplified. The common mode gain tells you how much the signals that are common to both input signals is amplified. Remember, we pretty much consider that to be noise, so we don't want that amplified, but we do want the difference between the two signals amplified. So ideally, the differential mode gain should be as big as possible, and the common mode gain should be as small as possible. But of course, you've got the same resistors in both gain equations, so you can't make one really, really big and one really, really small. You just sort of have to have a trade-off there. The common mode rejection ratio is the ratio of the differential mode gain to the common mode gain. This should be even larger than the differential mode gain. You can either take the magnitude of the differential mode gain and divide by the magnitude of the common mode gain, or if you convert the differential gain and the common mode gain to dB, which often is done, you can just subtract the dB value of the common mode gain from the dB value of the differential mode gain, and that will give you the common mode rejection ratio in dB.